Everyone, in this video we will start with the third module, that is introduction to Opamp. Opamp means operational amplifier. So this operational amplifier is nothing but it is a very high gain directly coupled negative feedback amplifier. Okay, it means it's a negative feedback amplifier. It's a feedback amplifier which can amplify the signals which are having wide range of frequencies. Earlier it was actually made, or it was actually designed so that it can perform some mathematical operations like addition, subtraction, integration, multiplication, differentiation, and many more operations. Hence it is being given the name operational amplifier, and later it got added with the some extra terminals. That's why it can perform varieties of other applications such as signal amplification. It acts like a filter, oscillators, regulators, comparators, etc. This is how the schematic symbol of an operation amplifier looks like. So it has two terminals, namely the negative terminal and the positive terminal, where the input voltages V1 and V2 are given to the terminals and output is the V0, and it has two supply terminals, that is the power supply terminals, namely the VCC and VEE, right? So the negative terminal is called inverting terminal and the positive terminal is called the non-inverting terminal, which means whenever the input is given to the inverting terminal, the output will be the inverted version of that. And non-inverting means whenever the input, a sinusoidal input, is given to the input, the output remains same as the input. I'll just show you here how it looks. So you are giving the sinusoidal voltage like this at the input, the output will be inverted like this, which is out of phase. So it comes like this. This is the meaning of inverting input. So where the output will be inverted to that of the input. And non-inverting means whenever you are giving the sinusoidal input like this, the output remains the same. That is non-inverting. In other words, here the output is 180 degree in phase, out of phase with the input. Here in this case the output is in phase with the input, no phase shifting, right? So coming back to here, the plus sign is the non-inverting and negative is the inverting terminal, as I told you. So which also means that output V0 is in phase with the input if the signal is connected to the non-inverting terminal, and V0 is out of phase if the input signal is connected to the inverting terminal. And these two are the supply terminals, as I told. And basically there are three packages in the op-amp. One is called dual line in package, DIP. Second one is the flat package, and third one is the metal can package. Okay, now coming to the equivalent circuit of an op-amp. So it's just written in the same manner like this. Okay, so V1 and V2 are the input terminals, and it has an input resistance which is called as Ri. It has some resistance in between this. So here VID, this is nothing but the potential difference between the two inputs. One, you know that one input voltage is higher than the other input, so therefore the potential difference exists. So you are providing there exists a potential difference between these two inputs. And the output, for the output resistance is present, which is with respect to the ground, that is the common ground. So this is called as R0, which is nothing but the output resistance, and it also has the two terminals, that is the supply terminals, VCC and plus VCC and minus VEE. See, the equation V0 is given by A into VID. So VID, as I told you, it is a potential difference between V1 and V2. That's why it is given as V2 minus V1. It can be V1 minus V2 also in the case when if the V1 is higher than V2. And what is A? A is nothing but the gain of the op-amp. Okay, gain, it is called as open loop voltage gain, right? So these are the things which you need to understand in this. Now coming to the equation. Okay, if you compare to the equivalent circuit, the output voltage you saw was V0 is equal to A into VID, where A is the open loop voltage gain, as I told you, and this VID is nothing but V2 minus V1, right? So VID means difference input voltage, V2 is the voltage at the non-inverting terminal with respect to ground, V1 is the voltage at inverting terminal with respect to ground, right? So this is the voltage at non-inverting and this is the voltage at the inverting terminal. So it is V2 minus V1. Every time the voltage at the non-inverting terminal will be greater than the voltage at the inverting terminal, right? So this indicates that the output V0 is directly proportional to algebraic difference between two input voltages. The op-amp amplifies difference between two input voltages. Therefore, the polarity of the output V0 depends on the polarity of difference voltage VID. So this equation is called the basic op-amp equation, right? Now we will just see there is a graphical representation of the equation which is shown here, where the output voltage V0 is plotted against the difference voltage VID. So this is the output voltage V0 which comes in the y-axis, and this is the difference voltage V2 minus V1, and the plot you get something like this. So this does not cross beyond plus VCC, nor it goes beyond minus VEE. So it remains within this limits itself. Right here it's given that note that the output voltage V0 cannot exceed positive and negative saturation voltages plus VCC and minus VEE. Therefore, the output voltage V0 is directly proportional to the input difference voltage VID until it reaches the saturation voltages, and thereafter it remains constant. So it becomes constant until certain level it reaches above, and thereafter it becomes constant. So this graph, whatever is showed here, is called ideal voltage transfer curve or the transfer characteristics of an op-amp, right? Then the open loop gain is very large, okay, and there is small difference input voltage VID. It will cause the op-amp output voltage to be driven all the way to its extreme plus Vsat. Okay, now from this transfer characteristics you can see that V0 is equal to A into VID, which is nothing but the basic op-amp equation, which is given as A into V2 minus V1. When you cross multiply, you get V2 minus V1 is equal to V0 by A. So A was in the numerator, it comes below. Ideally, the open loop voltage gain of an op-amp is infinity. So for an ideal op-amp, the voltage gain will be infinity. Therefore, this equation becomes V0 by infinity. Anything to the ratio of infinity, whenever the infinity is in the denominator, the output becomes 0. So V2 will be equal to V1 for any ideal op-amp. So it means that the inverting and non-inverting terminals are same potential with respect to ground. So whenever V1 and V2 are equal, you have to understand that the output voltage is 0. So ideally, for an op-amp, open loop gain A equal to infinity, input resistance Ri is equal to infinity, and output resistance R0 equal to 0. Now we'll just quickly go through the op-amp architecture, how the op-amp is usually made. So by seeing this block diagram, you can understand that it consists of the cascaded block, which consists of the voltages V1 and V2. So you are giving the differential voltage to the differential amplifier. Okay, so it's an amplifier, as I told you. Why is it called differential amplifier? Because it subtracts the voltages, that is the input voltages. So it's called as a differential amplifier. Then it goes to the high gain differential amplifier. So what is the meaning of high gain differential amplifier? So if the input is low, it amplifies the output to a very higher value. So that is a high gain differential amplifier. Then it has buffer and level shifter. Okay, and then it goes to the output stage or driver. So output stage or driver, in the sense, this is the place where you are getting the corresponding output depending on the inputs that you are given, which is given as V0. So you can see that there is explanation which is given here. The first two stages are cascaded differential amplifiers, and these are designed to provide high gain and high input resistance. I told you it gives you the high gain. The third stage consists of buffer and level shifter. So buffer is usually an emitter follower whose input resistance is very high. It prevents loading of the preceding high differential amplifier stages. Okay, Next, because of direct coupling, the DC level rises from stage to stage. This increase in DC level tends to shift the operating point of the active device used in the next stage. This in turn limits the output voltage swing and may even distort the output signal. This avoids problem of level shifter. Okay. So in the next video, we'll just continue with the op amp input modes and the further topics. Thank you.